A new way for nuclear fusion in condensed matter appears in 2020 following the publication in Physical Review C of the article Nuclear Fusion Reactions in Deuterated Metals. The article describes the experimental results and the phenomenological explanation of the research conducted at the NASA Glenn Research Center. The abstract of the article is reproduced here. I highlighted the main aspect of the research idea, that is, the possibility of activating fusion in condensed matter in those systems where the concentration of deuterons is extremely high and which have an electronic environment due to the metal, particularly favorable to their shielding. The search for energy-producing devices for interplanetary missions led to the discovery of the lattice confinement fusion at NASA Glenn Research Center in Cleveland. Lattice confinement fusion is a room-temperature nuclear fusion process that does not require large investment and technological complexity. What does it consist of? The concentration of a nuclear fuel nuclei in a magnetic confinement fusion and in inertial confinement fusion is about 10 to 14, while in lattice confinement fusion is about 10 to 23. This is practically the Avogadro number. Why? Metals like titanium and erbium, like palladium, are absorbers of hydrogen and its isotopes. In particular, erbium absorbs deuterium up to erbium-D3. The system is initially irradiated with 2.9 megaelectronvolt gamma photons, which produce the dissociation of deuteron into protons and neutrons. The energy transfer is from the neutrons to the static deuterium nuclei in the lattice, which are brought to an excited level D star. The electronic structure of erbium produces extensive shielding of a partially charged deuterium nuclei due to transfer of binding electrons to the F-band of erbium. This reduces the repulsion and promotes the fusion reaction rate. The process can take three different paths. In the BC process is a true nuclear fusion process, as helium-3 and a neutron are formed with an energy of 2.45 megaelectronvolts. The other two processes are transmutation processes. In fact, in the DE process, we have the transformation of erbium into thulium. This is called a screened Oppenheimer-Phillips stripping reaction because it is favored by electron shielding, or the real stripping reaction by Oppenheimer-Phillips, which is not a real transmutation, but is simply the passage from one isotope to the another with the production of a proton. This is a recently discovered process but contains points of contact with the cold fusion 34 years ago. They are metal saturated with deuterium from gaseous phase of deuterium. The system is a solid solution of deuterium metal. In cold fusion, this occurs by electrolysis in heavy water. The bond of palladium, titanium, erbium, and other metals with deuterium and hydrogen produces a transfer of electrons toward the metal, giving the system the property of a mixed conductor, electronic and ionic. In palladium, this has been evident since 1929 with the Kane effect. The numerous experimental data of nuclear phenomena and excess heat in cold fusion are found As the deuterium-metal ratio increases, the phenomena encountered in lattice confinement fusion with the erbium-deuterium-3 are in agreement with the elevated concentration of deuterium. Ultimately, cold fusion is nothing but a lattice confinement fusion. In 1989 and the following years, big science bitterly contested cold fusion. It's now good that NASA, Advanced Research Projects Agency Energy, and BEHIND have programs on low-energy nuclear reactions.